Okay, so it's my pleasure to welcome Markus Hunziker from Baylor University. He'll talk today about highest weight Harish-Chandra modules and classical invariant theory.
Thank you for the invitation. It's always a delight to speak in the University of Georgia Algebra Seminar. Several things that I present today have their origin actually in Boyd, so I was starting to think about things like this back when I was a postdoc at UGA. So let me begin. Something is not quite right. Okay, sorry. I thought it works, but I cannot shift. Let me check one more time.
You click
I
on it.
cannot move the pages. I need to. I don't know why this didn't work. I practiced before and I thought it would work, but
If you click on it, sometimes it helps. I don't know.
is that what it is? So otherwise, let me double check. All right. This is view. Okay, I think you're right. Okay, man muss immer mit den einfachsten Beispielen anfangen. This is a famous quote of Hilbert, which says, you always have to begin with the most simple examples. So my first example in this prelude is invariant theory of the simplest of simple groups, namely the group with two elements. So let's look at the following. And this is, by the way, inspired by the first paper in modern algebra, which was Hilbert's famous paper from 1890. I will say more about this later. So if you look at the action of the group plus minus 1 on, say, 3 variables, then the invariant ring would be the ring of even functions in these 3 variables. This ring of invariant functions would be generated by these 6 quadratic monomials. And what I will now do is I introduce a polynomial ring in 6 indeterminates corresponding to these 6 generators. So then I define, as usual, a surjective algebra homomorphism from this polynomial ring to my algebra of even polynomials, where I just sent this zij to the product xi xj. Now, this is not an isomorphism. It's obviously surjective, but not an isomorphism because there are relations among these invariant quadratic polynomials. So what are some of these relations? Well, for example, the polynomial z11, z22 minus z12 squared is in the kernel because if you substitute for it the corresponding quadratic polynomials, then you get identically 0. Similarly, if you do it for this polynomial here, you get, after substitution, identically 0. So more generally, what you get is that the kernel actually is generated by the 2x2 minors, so 2x2 determinants of submatrices of this symmetric matrix. Now you can ask, are there any relations among these relations, higher syzygies? Well, if you look at the following linear combinations of 3 of these 2x2 minors, you see that you also get identically 0. This is an easy exercise. And then you attain, and Hilbert did calculations exactly like that in his 1890 paper, you get what we would now call a minimal free resolution, where on the right here you have, can you see the mouse cursor, by the way? Or
Yep.
no? So this is the ring of even polynomials in x1, x2, x3. This is the polynomial ring in these C's, and these are some free modules over this polynomial ring. And maps between these free modules are given by the following matrices. Here I introduced some signs. I will not explain why I inserted these here, but the columns then of phi2 would be the relations among these 6 2x2 minors, and the columns of this matrix here would be relations among the relations among the relations, or something like that. And you can easily check that if you take any 2 maps here, you get the 0 matrix if you multiply them together. What is less obvious is that this is actually an exact sequence. What about the odd degree polynomials? Let's look at that. Now, the odd degree polynomials are, of course, not a ring, because odd times odd, if you multiply two odd polynomials, you get an even polynomial, but it's a module over the even polynomials, even degree polynomials. And you get again a minimal free resolution as an S module, where S is that polynomial ring with the z's. So here I sent the I standard basis vector here in S3 to the simplest simplest odd polynomial, which is just one of the variables. And this is this map here from S3 to F minus. And again, this map is clearly surjective, but it's not injective. And you have, again, elements in the kernel. For example, the vector, the column vector 0, -2, 3, z2, 2 is in the kernel, because if you substitute things in, remember that z2, 3, when you substitute things in, you get polynomial x2, x3. So this -z2, 3 lives in the second slot. So we also have to apply psi naught to E2, so which gives you this x2. And similarly for the last thing, z2, 2 goes to x2, x2, and then E3 goes to x3. If you multiply this out, you will get 0. And the kernel of psi 0 then is generated as an S module by the columns of the following matrix, psi 1. So there turn out to be 8 relations among these generators. It's a curious fact, and I completely understand this, but if you look at what the resolutions look like of the even polynomials and the odd degree polynomials, the maps are actually, these matrices are transposes. First of all, you see here is rank 3, rank 8, rank 6, and for the even polynomials were just the other way around. So this is a curious thing that's true in general for arbitrary many variables for invariance, for even and odd polynomials in arbitrary many variables. So one of the big goals of this talk is to explain to you how we can get these kind of resolutions in a systematic way. And I will explain what all these diagrams mean. This is sort of in the second half of the talk. So I will have a diagrammatic description of my minimal free resolutions. I call them .zip descriptions because they are sort of compressed for something more complicated. So let me say a few things about the numbers that I put in these boxes. So for example, there's a 2 in this box, because if I go from here to there, I lose a box with a 2 in it, and that will tell me that this map phi1, well, this is that matrix before that was called phi1. The entries were 2 by 2 determinants, so they were of degree 2. The matrix corresponding to phi2, so you see you're losing a box with a 1 in it. Those were given, well, all the entries of this matrix were of degree 1. And similarly for phi3, the entries were of degree 1. So these numbers have something to do with the degrees of the entries in these matrices. By the way, on all of what I looked at so far, there's an action of the general linear group in 3 variables. That has to do sort of the x1, x2, x3. There's a GL3 action going on that commutes, of course, with the group which sends x1, x2, x3 to -x1, -x2, -x3. So GL3 acts on everything. And what I will actually get is a GL3 equivariant minimal free resolution. Let me just remind you a few things. So the S was the coordinate ring of, or you can think of it as the coordinate ring of symmetric 3 by 3 matrices. So GL3 acts on that. And these are the usual oops, sorry. These are the usual Young diagram. I cannot use my mouse. It will flip through the pages. So these white diagrams there, these are standing for irreducible representations of GL3. You can get from that .zip, this compressed resolution, to the real resolution by sort of expanding things. First, for these diagrams, you glue two of these diagrams. The diagram together with its transpose, you sort of stack them together sideways like this. So you, for example, for this diagram, you get this this little diagram, and then you're just expanding the columns. So you have a 2 and a 1. So a total of 2 plus 1. You have 3 white boxes here down in this Young diagram down here. Another 3, a column of height 3, and then 1 plus 1 is 2. So this would be a column of height 2. Similar here. So if you stack them together, you have 2 1s. So there's a column of height 3, then a column of height 2, and a column of height 1. So this compressed resolution encodes this GL3 equivariant minimal graded free resolution. Just a sanity check about the ranks of these free modules here. If you look at the numbers that show up there, so they have to do with the dimensions of the corresponding GL3 representations. So if you recall, the dimensions of GL3 representations you can find by counting semi-standard Young tableau. So we have this is a 6-dimensional, represent a 6-dimensional representation of GL3 because you have 6 semi-standard Young tableau right there. And similarly, you have an 8-dimensional representation here and a 3-dimensional representation there. How about the maps that the differentials in these resolutions? Can you describe them explicitly? And yes, you can. This has to do with the following. So S, again, this is the coordinate ring on the 3x3 symmetric matrices. So as a GL3 representation, this is very classical. This has a multiplicity-free decomposition with these diagrams like that. And these maps in the resolution that I described earlier, which I write like this, they all come from embeddings of multiplicity-free components using the Littlewood-Richardson rule. So for example, this map that I called phi3 earlier, you see here you're losing these 2 boxes. So the highest weight component here embeds into the tensor product of this guy in S together with that diagram here. So this is a multiplicity-free component. It's sort of related to the Peary rule, if you know what that is. And then how this diagram here sits inside this tensor product with multiplicity 1. So then you have a canonical map that sends this representation into this tensor product. And all the maps that I showed earlier arise in this fashion. Actually, all the maps in all the resolutions that I will throw out later will arise in this fashion. So this is something very nice. So you can explicitly describe these maps if you choose spaces for representations and stuff. You can write down matrices if you want. Similar for the resolution of the odd degree polynomials. I will not explain this now, but a convenient way of interpreting these resolutions or information to extract from these resolutions are well, what people call in syzygies Betty tables. Not going to explain this in detail, but you reorganize these diagrams in sort of a useful way. If you add a box with a 1, you would just continue in the same row. If you add a box with a 2, you will go 1 row down. So from these diagrams with the degrees in them, I can place them sort of in a in a table. And from this, if you know the dimensions of the corresponding GL3 representations that correspond to these diagrams here, I can write down the Hilbert series. So this guy will correspond to a one-dimensional representation. This guy, after this unzipping, corresponds to a six-dimensional representation. The z's really should have degree 2 because they correspond to quadratic polynomials. So there's a doubling of degrees. So that 2 becomes a degree 4 thing. Here this is a degree 3 thing. Anyway, so multiply that by 2, you get a 6. So you get the numerators of these Hilbert Poincare polynomials. If you expand it out, this would be the Poincare series of the even polynomials and this of the odd polynomials. And if you add these two together, you will just get the Hilbert Poincare series of all the polynomials in 3 variables. F plus and F minus, these two spaces we looked at are Cohn-Macaulay modules. A hint for that is that the Hilbert series here have positive numerator. When you have Cohn-Macaulay modules, you can write down so-called Hironaka decompositions. So you can view them as free modules over some polynomial subring. If you look at the polynomials x1 squared, x2 squared, x3 squared, then F plus actually can be written as a free module over this polynomial ring. These are homogeneous systems of these form a homogeneous system of parameters, and you can write F plus and F minus as free modules over this ring. And from that, you can immediately read off the Hilbert series too. So this is a recent result of mine with a postdoc at Baylor, Will Erickson, that we can write down, well, not Hironaka decompositions, but so-called Stanley decompositions for all the things that I'm going to write down later. By the way, why do I call it F plus and F minus? This has something to do with representation theory, namely the F plus and F minus. These are the two components of the so-called oscillator representation. And one of these models for this oscillator representations are on polynomials. This is called the Bargmann-Fock model. So the Hilbert space of the oscillator representation is a completion of a polynomial ring. And the decomposition into these irreducible representations correspond to the even and odd polynomials. I will not talk more about this, but since this is an algebra seminar, but I will talk about Harish-Chandra modules later on. So let's start from scratch after the prelude on classical invariant theory. So suppose you start with a reductive group. Think of a general linear group, a special linear group, or an orthogonal group. For most of my talk later, it will be the orthogonal group. Let W be a finite dimensional representation of H. Think of something that's made from V. This sort of the natural representation, like a bunch of copies of V and a bunch of duals. Or if you're really a classical invariant theorist from the, say, 19th century, you would have looked at forms of a given degree on V. So these are the kind of representations for now that we look at. Then you introduce this notation here, CW super H here. This is the ring of invariant functions, invariant polynomial functions on W. So that's a C algebra. Something else that classically people have looked at, and this is sort of modern terminology, but about some very classical things, is the module of covariance of a given type. So if U is any other finite dimensional, usually irreducible representation of H, you can look at the H equivariant polynomials. So polynomials from W to U that commute with the H action. If U is the trivial representation, then this would just be the invariant polynomials. But this thing, which I write like this, is a module over the invariant ring always. Let's link this up with the example from the prelude. if V is the representation of the group plus minus 1, so the natural representation of the group plus minus 1. So the group plus minus 1 is an orthogonal group. It's the orthogonal group in 1 dimensions. And then if you look at W, 3 copies of this natural representation, so this is a 3-dimensional representation. So then the invariant ring is what I used to call F plus, and the module of covariance of odd degree polynomials. These are the covariants of type V. So there the group acts sort of according to the sign. So this is an example of a module of covariance, the odd degree polynomials for the simplest of simple groups. Simple group. Yes.
Oh, never mind. Sorry.
A question?
The question is what you just wrote on the slide. Never mind. So, yeah.
So in Hilbert's paper from 1890, he showed, well, not in this generality, but his proofs actually prove much more than what he considered, is that if you start with this reductive, with a reductive group, such as GLV or SLV, then this invariant ring is always finally generated as a C algebra. So you can think of this invariant ring as a quotient of some polynomial ring. You can make this quotient map homogeneous if you give these z's at certain degrees. So, but we will not really labor on this detail. Similarly, these modules of covariance, they are finitely generated S modules. So this is under the hypothesis that H is a reductive group. He also introduced syzygies. He proved the syzygy theorem, which says that both these kind of invariant rings admit finite free resolutions. The length of these resolutions is actually bounded by the number of generators of that invariant ring. So this was absolutely revolutionary. Unfortunately, in some sense, it was critiqued by some of the contemporary mathematicians that these things were not constructive. This led the king of the hill at that time of classical invariancy, Paul Gordon, to exclaim that this is not mathematics, that this is theology. We can make a lot of things now much more explicit. Hilbert himself followed up with another paper, by the way. Shortly after this paper, he proved a second paper where he tried to address Paul Gordon's critique. And in the second paper, he introduced the Nullstellensatz. Anyway, so to make things more constructive. So it's phenomenal just what he did in these two papers. So he laid sort of the foundations, what then later became modern algebra, which sort of took its form with Emmy Noether, but a lot of it is already here in Hilbert's paper from 1890, like Noetherian rings, etc., and the syzygy theorem too. So in the following, I now will look at a special case of this situation where H is one of these 3 classical groups, and W is a bunch of copies of duals of V and V. In the orthogonal and the symplectic case, the dual is isomorphic to V. So I can just look at a bunch of copies of V. So then Weil's first fundamental theorem for these 3 groups says that the invariant ring is generated by sort of the obvious invariants, namely, well, for example, for the orthogonal group, the dot products, if you will. So the dot products of a bunch, you take the ith vector and dot it with the jth vector, that's an invariant. And then the theorem is that these obvious invariants generate the invariant ring. What about relations? Well, the relations are addressed in the second fundamental theorem. And this links directly up with what we had earlier with in our prelude, that the relations among these generators are given by the k plus 1 times k plus 1 minus of a symmetric matrix. So the kernel of this map would be, well, the coordinate ring of some, well, anyway, so this invariant ring becomes sort of isomorphic to the coordinate ring of some determinantal variety. By the way, k for me here is the dimension of V, and n is the number of copies you have. It will be clear why I make this somewhat odd choice in what I say later. So if k is greater or equal to n, so again, this is the dimension of V is greater than the number of copies, then the invariant ring actually is a polynomial ring. But if k is less than n, then it is not a polynomial ring. So can you do the same thing for modules of covariance? Can you find explicit generators and relations for modules of covariance? And I will address this by using how duality. Usually people don't think of how duality in that way, but I will use how duality to address these classical problems of invariant theory. And for the sake of simplicity, I will only consider the orthogonal group here. The other groups are just the same, basically. I just want to keep it a little simpler. So now there's, for the first time, you have some real Lie groups entering the picture. So GR is this group, which you should think of as like an analog, sorry, of SU11. SU11 is sort of essentially the holomorphic automorphisms of the unit disk, which is here isomorphic to SP2NR, this group. Think of this as SL2R. So the KR is a maximal compact subgroup, which is the unitary group UN. This is an example of, this GR is an example of what I would call a group of Hermitian type. So GR modulo KR is what is called a Hermitian symmetric space, a complex space on which GR acts as holomorphic transformations. Actually, here you can think of this space as an open domain in the n-by-n matrices, and the group acts just by linear fractional transformation. So this is not important in what follows, but this sort of explains some of the terminology here. The complexified Lie algebra of this real Lie group is just SP2N. You can think of this as a generalization of SL2 over the complex numbers. And this Lie algebra has a natural triangular decomposition. In the following, this will be called P minus plus K P plus, where the P minus K and P plus are the following subalgebras, Lie subalgebras. The K is just the Lie algebra of GLN, which is sort of funny, embedded here diagonally embedded as A minus A transpose. Now, to prepare for how duality, I have to introduce a certain Lie algebra embedding of this Lie algebra G into invariant differential operators on my space from Weil's theorem W. So let dW be the invariant, not invariant, the differential operators on W with polynomial coefficients, so a Weil algebra, if you will. Then how recognized you can embed the Lie algebra G into the invariant differential operators on W, such that the image generates these invariant differential operators as a C algebra. Natural generators for the invariant polynomial differential operators would be, well, the multiplication operators given by the canonical invariants, the Fij's, as I called them earlier. Then things like this, Weil would have called these differential operators polarization operators. And then you have quadratic invariant differential operators sort of related to the Laplacian, right? So explicitly, that Lie algebra homomorphism or embedding is given as follows. So So a matrix in this Lie algebra G goes to these differential operators. So this is a Lie algebra homomorphism. The eta here is a parameter that you can choose for your convenience. So for any eta, you would get a Lie algebra homomorphism. I will choose eta to be 1/2 for the following reason. So this the P minus Lie algebra can be identified with the dual of P plus via the following map. So a matrix in P minus, you can view it as a linear function on P plus by using the trace. Like this is well defined, and you can this establishes an isomorphism between P minus and P plus. So then if you think of SP minus, the symmetric algebra, as something in the universal enveloping algebra of G, this omega embeds ZP plus in the invariant differential operators, and it's precisely consistent with what I had earlier, the syzygies. So C here is a symmetric matrix, is sent to the basic invariant function, this dot product here. So Zij goes to Fij. So everywhere that, well, using this Lie algebra homomorphism, then I can view this polynomial ring on W, the coordinate ring of W, as a representation for the Lie algebra. Now, let's look at the decomposition of this polynomial ring. So the constituents of the representation of H realized on the polynomials on W, well, these modules of covariance you can identify with the homomorphisms of the duals of these U's into the coordinate ring of W. So I write sigma for sort of the H spectrum. These are the things that actually show up such that there are covariants. So polynomial maps from W to U that are H equivariant. I also introduce so-called K-dominant integral weights. So these are n tuples of complex numbers a priori, such that their successive differences are always non-negative integers. So this is related to that the K, this was a GLN. So this is like a highest weight of a GLN representation. Okay. Now, a famous paper by Kashiwara and Verne introduced what we would also call Howe duality, namely an injective map from this set sigma to these K-dominant integral weights, which I denote by sigma goes to lambda, such that the covariance of type U sigma are actually as a module for G via this map that I introduced earlier with the differential operators, that this is a simple module for the Lie algebra G. So remember, this Lie algebra G now acts on the polynomials on W, and it commutes with the H action. So this, at least on the face of it, makes some sense. But this is an irreducible or simple module for G. It's actually a simple highest weight Harish-Chandra module for an infinite dimensional unitary representation of the metaplectic cover of my group GR. Every unitary representation, well, every unitary, I should say, highest weight module representation of this double cover arises in that way. So this was the main result of that famous paper of Kashiwara and Verne from '78. This map sigma to the K-dominant integral weights can be given explicitly. You note here that there are some half integers. So these are in general not integral weights. They are K integral, but not integral for G. Let me skip over the next part. Well, maybe I should say just a little bit something. The K action, which is the GLN action and all of this, is not quite a standard action, but it's twisted by this one-dimensional representation. So minus k over 2 omega n. So that's the thing what you would get when you have zeros everywhere for the sigmas. So this is a one-dimensional GLN representation. So you can twist it. You can twist everything by this one-dimensional representation for GLN. And you would get the standard action that people would have considered, like Weil would have considered on things like modules of covariance. But these modules of covariance are now highest weight modules for this Howe dual Lie algebra G. In the following, a parabolic subalgebra of G plays an important role, namely the K plus P plus. The K is this Levy factor isomorphic to GLN, and the P plus is this thing in the upper right corner, which is an abelian Neal radical of a parabolic subalgebra with Levy Lie algebra K. This simple module L lambda, you can view it as a module in what people would call the parabolic BGG category O, and then OQ, where Q denotes that parabolic. And L lambda in this category can be viewed as a quotient of what we would call a parabolic Verma module. This is a module where you induce the finite dimensional K representation. Well, you first view the finite dimensional K representation F lambda as a representation of this parabolic by just letting the Neal radical act trivially. So then you have a UQ module, F lambda, and then you reduce to G, you get a G module, and this is a parabolic Verma module. It's a quotient of the usual Verma module with highest weight lambda, but this is a parabolic Verma module. There's an easier way to think about these n lambdas, namely because of this triangular decomposition, P minus plus K plus P plus, you can view this n lambda as a tensor product over the complex numbers. This is a tensor product over C, where you take the SP minus, and on the right is just the F lambda. So these can be viewed as polynomial functions from P plus via our identification earlier to F lambda. So these n lambdas are very simple modules for S, like the S being the symmetric algebra on P minus or the polynomial functions on P plus. Namely, they are free S modules of rank equal to the dimension of this finite dimensional module. In 1991, Davidson, Enright, and Stanke proved that there exists an exact sequence where here is the simple G module. This is just the quotient map from n lambda to L lambda. And here, this would sort of describe the relations here, right? In the first term in the resolution is the relations among the generators. And this map psi1 can be explicitly described. If I would introduce Young diagrams, it would be described in terms of some embedding of a multiplicity-free Littlewood-Richardson component, but they would have formulated it more abstractly as a PRV component of some distinguished subrepresentation of S. These gammas are Harish-Chandra strongly orthogonal roots, but everything is very canonical. When I was a postdoc in UGA, I generate, well, with Enright, I proved that all these kind of representations actually have minimal free resolutions that are BGG resolutions for G. But what I didn't know at that time was sort of how to describe these. Everything was pretty abstract at that time, but I was able to produce the whole resolutions, not just this tail of the resolution. But I wouldn't have been able to describe all the maps. With recent results, I can actually describe all these maps also. And this sequence here, I guess it's shorter than a short exact sequence. This exact sequence can be then used to give all the explicit generators and relations for my models of covariance. If I would do this for H equal to the group plus minus 1, I would get what I did in the prelude. So now sort of the main event is to talk about diagrams of Hermitian type. So Harish-Chandra studied, of course, representations of real Lie groups. And one of his great accomplishments is sort of to reduce sort of analytic things to algebraic things, where he associates to a certain nice class of representations of Lie group representations, so-called GK modules. So these are just, so G here is the complexification of the Lie algebra of this real Lie group. By the way, here I assume GR is simple, non-compact, connected, and finite center, which will make it real reductive. And KR is a maximal compact subgroup. So the G is the complexified Lie algebra. The K is the complexified group, which is a complex reductive group. So this functor is given by going to the so-called K finite vectors in a representation, and this can be studied. These corresponding Harish-Chandra models can be studied by sort of more algebraic methods. And mostly I work in the algebraic side of representation theory. A famous result also of Harish-Chandra is that there exists infinite dimensional highest weight Harish-Chandra modules. So these are highest weight modules, so quotients of Verma modules, if and only if this GR mod KR is a Hermitian symmetric space. So similar to the example I looked at earlier. From now on, GR mod KR is always a Hermitian symmetric space. Here's the classification of Hermitian symmetric spaces. You can give that in terms of what are called Vogan diagrams for these real Lie groups. You can also think of these, if you remember this parabolic subalgebra Q, which is K plus P plus. So you can view these diagrams where the white dots for these parabolic subalgebras, where the black dot, the white dots are giving you the Dynkin diagram of the Levy factor, and this is sort of the thing you're omitting. So this is, these parabolic subalgebras are all maximal subalgebras of co-minuscule type. So as I said, there are these parabolics of co-minuscule types. This triangular decomposition is just as we had it before in our special case. An important object for me is the so-called poset of positive non-compact roots. So these are the roots such that the root spaces are in P plus. And these posets are very, very nice. In fact, Jacobsen showed in '83 that the Hasse diagram of these posets of non-compact positive roots are planar, and they can be drawn at a two-dimensional orthogonal lattice. Let's look at a simple example of SU32. So this P plus is this set of matrices. And so each of these stars here corresponds to one of these roots in phi P plus. This would be, this star here at the bottom left would be the simple non-compact root, epsilon 3 minus epsilon 4 in standard notation. This star up here is the highest root, epsilon 1 minus epsilon 5. And these numbers between the dots, so each dot corresponds to one of these roots. And this would be alpha 3 plus alpha 2. Alpha 2 would be a compact simple root. So alpha 2 plus alpha 3, that would be epsilon 2 minus epsilon 4. So that's one way to visualizing these posets here. We can do this for other types, for type C and type D, and also for exceptional types, where the root at the bottom is always the simple root corresponding to the black node here in the Dynkin diagram. And the top is the highest root. I have again these k-dominant integral weights, and as usual, rho is the half sum of positive roots. These are the positive roots in G, not in K. And an important definition that I introduced is the following. For any k-dominant integral weight, I associate to this lambda a certain poset, namely the set of all roots in Vp plus, such that if you take the inner product of lambda plus rho with the co-root alpha check, you get a non-positive integer. These diagrams y sub lambda turn out to be lower order ideals. I will explain that in a little bit, of these posets Vp plus. So these lower order ideals can be viewed as generalized Young diagrams. For example, if you're looking at lambda plus rho given like this for SUP4, if you look at all roots that give you a non-positive integer on lambda plus rho, you will select these roots. For example, alpha, what is it? Epsilon 5 minus epsilon 6 here is in this diagram because, well, -2, -2 is negative. So that's in there. The highest root, which would be epsilon 1 minus epsilon 8, is not in it because 3 minus -3 is positive. So I'm just looking at the things where it's negative. So this, if you turn it by the appropriate amount of degrees, I guess 135 degrees clockwise, you will get a Young diagram like this. So a lower order ideal means if you have anything in this poset, then everything below it will also be in it. So that's a lower order ideal. These lower order ideals can be used to describe regular integral blocks in this parabolic category OQ. For example, for this real Lie algebra, or if you want maximum co-minuscule parabolic, if you look at all lower order ideals corresponding to the weights in the so-called block of this lambda plus rho, here lambda is the highest weight of a certain spin representation, you will get a nice a nice description of all these highest weights in this block in terms of these diagrams y sub mu, where mu is anything, where mu plus rho is in the Weil group orbit of lambda plus rho. So using, I also introduce numbers to put into my diagrams. So for example, I put a 2 in here. So if you would, from this node, from this highest weight plus rho to this highest weight plus rho, I would apply the reflection in epsilon 3 plus epsilon 4. And this here is what I have above, minus 2 times epsilon 3 plus epsilon 4. So because the multiplicity in front of this reflection, how many times you have to subtract a root, that's what these numbers are. From each node to the next, you apply a reflection, and the additional box sort of keeps track of how many times you have to subtract a root to make it down, this poset. You can also use this to compute Hilbert-Poincaré series of the finite dimensional representations for these of this Lie algebra. For example, again, when lambda is this spin representation, and I do the same thing that I did before. These are the Betti table in the sense that I explained earlier. These dimensions here are the dimensions of K representations, which would be GL4 representations that I have had earlier. Since this is a finite dimensional representation, this is a dominant integral weight. So L lambda is finite dimensional. So the Hilbert-Poincare series is actually a polynomial. So everything here cancels in the denominator, and you get a polynomial. So this is a certain graded, well, the grading, by the way, comes from the central element in K. But you get something like this for all finite dimensional representations in these Hermitian symmetric settings. In fact, so if you have a dominant integral weight lambda, if you define di, these are basically the coefficients in terms of the fundamental weights plus 1. Then if you place them in these diagrams, the rotated diagrams, which correspond to these lower order ideals, so you get certain degree diagrams analogous to what I had up here, but for arbitrary Hermitian symmetric spaces. And notice that I highlighted some in a little darker color, and you see sort of the Dynkin diagrams embedded into these diagrams. Like here would be for E7, that would be the Dynkin diagram for E7. So using these diagrams, you can describe resolutions of all finite dimensional representations. But we are, of course, interested in infinite dimensional representations. So to do that, there is something called Enright-Shelton reduction, which allows you to, and this is very unique to Hermitian symmetric settings, to reduce singular settings and non-integral settings into the regular integral case. So I introduced the following posets. So this is a mouthful, so I probably will just glance over it. So if you start with a K dominant integral weight, so this psi sub lambda, these are the so-called singular roots in phi p plus. So roots that are orthogonal to lambda plus rho. S is the number of these singular roots. And then I call that phi sub lambda s of p plus. These are a bunch of roots that are giving you integers here with lambda plus rho that are orthogonal to the singular roots. And there's this extra condition that Enright introduced, that alpha has to also be short if there exists a long singular root. This is a generalization of things like integral root systems. Now, these sets of roots, it turns out, are always posets of this form for some other Hermitian symmetric pair. Let me illustrate this in a few examples. For example, consider lambda plus rho for SU43 here. I highlighted in red, this is a repetition of a number, 2 and 2, that corresponds to a singular root, epsilon 3 minus epsilon 6. Epsilon 3 minus epsilon 6 is orthogonal to this lambda plus rho because of this repetition. So if I remove everything that's not orthogonal to this red dot corresponding to this singular root, I end up with this diagram, which is isomorphic to this diagram of positive non-compact roots of SU32. So this is something of smaller rank. And this happens for all types. Here's an example in type C. So you have a root that's singular, epsilon 3 plus epsilon 5, because I have a 2 and a negative 2. And if I remove everything that's not orthogonal to it, I get a diagram that's isomorphic to something of smaller rank. Here is an example where I have a long singular root, 0, that 0 here makes this highest weight singular for the root 2 epsilon 4. All these roots on the right edge are long roots. So then if I remove all the things that are not orthogonal to this red dot and are short roots, that was part of my definition, then I have to delete also all the long roots. But this time it switched to the type because now I have only short roots, and I switched from type C to type D. So when you do these sort of things, you can switch from type C to type D. Now, if lambda is the highest weight of a unitary representation, so that's unitary for my real Lie algebra G sub R, then if I remove all the roots that are in the diagram associated to this lambda, then again, this happens to be a poset of the same type. And this poset here describes these diagrams that I had earlier in my talk, including the prelude, these gray diagrams that keep track of the resolutions. Here's a quick example. So when H is O4, the orthogonal group in 4 dimensions, and G is SP6, so this means I'm looking at 6 copies of the orthogonal of the natural representation of O4. So under this Howe duality, that if sigma is this representation of O4, the corresponding weight under Howe duality is this lambda with lambda plus rho equal to 4, 3, 2, 1, -1, -5. So that how you do this is via this Howe dual thing, the theorem of Kashiwara and Wern. You notice that this is a singular highest weight. So you get rid of this by doing this reduction. So then you still have this -5 here. This -5, if you have any root, this would be in type D. Well, any root here in type D4 is, sorry, one more time. I'm almost done. So this -5, if any root that involves epsilon4 gives you an inner product that's negative. For example, well, 2 epsilon4 check. If you take the inner product with that one, you get a -5. So that would be negative. Epsilon3 plus epsilon4, the inner product would give you something negative because 2 minus 5 is negative. Also, epsilon1 plus epsilon4 with this weight is negative because 4 minus 5 is negative. So I have to remove all these negative things. That means you're removing all the roots that have epsilon4 in them. Then you end up with a further reduced weight, which is something for type C3. And again, the diagram here, the degrees that I put in these boxes are as usual. So I put a 2 in here because that thing corresponds actually to 2 epsilon3. So that's corresponding to this 2. Then the next simple root is epsilon2 minus epsilon3. So that gives you, because the difference is 1, I put a 1 here. And because epsilon1 minus epsilon2 also here, 4 minus 3 is a 1, I put a 1 here. The way these diagrams worked, as I showed you earlier, this is how you have to fill out these degree diagrams. And this gives you, as before, completely the resolutions, or as I call it, the compressed resolution. And you can decompress everything, uncompress, unzip it. And by putting things in a Betty table, you can compute Hilbert series. If you translate it back to the module of covariance stuff, this gives you Hilbert series for all these modules of covariance. And all the syzygies if you write down what the maps would be. So using these diagrams, so we can then compute the syzygies and Betty tables and Hilbert-Poincare series of all these modules of covariance in the context of Howe duality or Weil's fundamental theorems. I can compute things like the depth and the dimension, whether something is Cohn-Macaulay. These modules are not always Cohn-Macaulay. And this was also the starting point for much, much more. Namely, we can write down explicit linear bases for all these not just Cohen-Macaulay models, but all models of covariance. I can write down explicit linear bases, including surprising things that you would think would be known for a long, long time. Linear bases for very classical things like invariant tensors for all these 5 groups we can do by using all this machinery. So this is related to some recent preprints. Most of this is work with Erickson. What I talked about today is something that's still under construction, but this will be this big paper here with Erickson and a former student of mine, John Miller, and Mark Sapansky. Diagrams of emission type I introduced earlier in 2014. This actually is an outgrowth of some lectures I gave at Georgia, at UGA, in 2010. Was the first time I introduced these diagrams. But this developed in a lot more, and I can now calculate pretty much everything in classical invariant theory using these diagrams. So that's all I had to say.
Can you hear Dan?
I can hear you, yeah?
Can you go back about 3 slides?
This one?
So when you take L lambda, so presumably you can associate.
I cannot really hear you. Can you translate it later, or?
So with L lambda, presumably you can associate some algebraic variety to them using the ring. Is that correct?
I didn't hear the question. Will, did you hear it? Or Scott, can you?
He was asking if you could associate some algebraic variety to that, I believe.
Oh, yes, that's correct. Yeah, the associate variety of that L lambda is actually, so you see this reduction here? Yes, that's correct. So the 18 is the dimension of the determinantal variety of all symmetric 6 by 6, because we are dealing with 6 by SP6, 6 by 6 symmetric matrices of rank less or equal to 4. That's the associate variety of that L lambda.
So for any L lambda, you can associate a variety whose order of the pole is going to be the same.
The order of the pole gives you the dimension of the associate variety. That's correct. And this, by the way, should have not been a 2. This should have been a 1. It's this 1 minus t. So by the way, from here to there, there's different conventions for degrees. The z's, they should be really considered as having degree 2, but here I viewed them as degree 1. And the highest weight vector here was, by definition, in degree 0. Whereas if you think of modules of covariance, this would be in degree 5, the number of white boxes here. By the way, the associate variety, this was worked with Roger Zero and two Chinese collaborators. I can read off of out of the diagram that I introduced, I can read off the associate variety of all these L lambdas directly. It's actually, these associate varieties this is in this paper here. We show that the associate variety is completely determined by just the width, the so-called width of a poset. It's rather elegant, actually. By the way, Bill, it's quite, that I recommend that you look at this paper, Bill.
Okay, I will.
Because it includes there's a lot of relations between how many of these lower order ideals there are and dimensions of Springer representations and things like this.
Well, I was going to say, as you probably know, these lower order ideals are actually inversion sets of minimal elements in the Weil group, right? Coset representative.
Correct. Yeah, that's correct. I did this in all of that is explained in this paper too. That's right. That's what I lectured on in 2010 at Georgia.
It's not fresh in my mind, but I'll have to.
But that's right. But I did talk about these minimal length coset representatives. But all of this is sort of a systematic way, and everything works uniformly across all types, including these unitary representations for exceptional groups. And
Now, at one point you put the fact that they were unitary as some hypothesis. Is that just so you can invoke some big theorems?
This theorem here would be wrong in general. So it would be correct if you replace unitarizable by constant modules. But constant modules are these highest-weight Harish-Chandra modules such that all the Kashtan-Lustig polynomials are 0 or 1. So these guys these correspond to sort of smooth or rationally smooth Schubert varieties, and they actually have resolutions. Brian Bow and I sort of described some of that in a paper of ours. But yeah, every unitarizable representation is a constant module, and because of that, it has a resolution. In general, I do not, for arbitrary highest-weight Harish-Chandra modules, I can compute a lot of these invariants, for example, associated varieties, etc. But I cannot compute resolutions because, yeah, this machinery will not work if you don't have if it's not a constant module.
I see. Okay.
It has to do with Kashtan-Lustig theory that this works. Yeah.
So I have another question. So back to the same slide.
This one?
So in the superalgebra case, we have something like this, where we can actually define support varieties for these reducibles. Correspond to the atypicality for the weight. And the atypicality is a combinatorial invariant defined by Katz and Wakimoto. So is there like a combinatorial description for the order of the pole?
Yeah, it's something I still don't quite understand. A lot of, I'm working here. All that I'm doing here is very, very similar to the super case, actually, right? SUPQ and GLP, vertical bar Q, and all these kind of things, they seem very much related. So I have talked to some people related to this, but I haven't been able to make the connection between the real groups versus the short answer is I don't know, but it's very intriguing. I'm aware that very similar results hold in that setting, right? There, the dimension, the representations are finite dimensional, correct?
They are, but like we're working with infinite dimensional representations now, and similar types of formulas should actually work out.
Okay. But it's super. There's something to be discovered here, like all these infinite dimensional representations for these real groups, and then the supersymmetric situation. There must be some kind of a dictionary between the two, but I don't know the dictionary. That would be very interesting to me.
Okay, thanks.
Let's thank Markus again.